Welcome back, AP Statistics, to part 2 of chapter 3. We're going to talk about the shape of a set of data and talk about the mode or the modes. So do the data have bumps? We have a dot plot over to the right, and we see that we have a bump here and a bump down here and maybe a bump over here. Is this a bump in the data, or should we conceive of this as just one big mountain on the left-hand side, right? The x values that correspond to the peak of the bump are called modes, all right? So we have a mode at about 122 seconds, it looks like. Here's 120, here's 130, 122 seconds winning the Kentucky Derby. We also have another mode over here at about the 157 second mark, somewhere in this neck of the woods. This we would consider another mode, right? Now, why is that? A mode is a class with the greatest frequency in its vicinity, and vicinity is not a very objective term. But this is one of the aspects of statistics in which you just need to use some, you might call it instinct, you might call it common sense, but this is the most populous class in its vicinity, and there is a drop-off to the right and especially to the left. This class of 122 seconds has a steep drop-off to the right and left, and so it is another mode. But what about over here? Well, we can talk about that in just a moment. But let's talk about situations that we could run into regarding the mode. If we have one mode, that is unimodal, all right, makes sense. Two modes, bimodal, all right, uni meaning one, bi meaning two. And then if you have three or more modes, we don't say trimodal or something like that, we just say multimodal, all right? So the big question here is this graph here bimodal or multimodal? Do we have two bumps or 1, 2, 3 bumps? All right, how should we interpret these data? So we're going to describe the data below in terms of its modes. We've already done that. There's a mode at 122 seconds, and there's a mode at about 157 seconds over here, and maybe, just maybe, a mode between 128 and 129 seconds, okay? Now, why might we want to consider this guy a mode right here? Well, the racetrack condition was not color-coded last time you saw this, but we do have a color coding this time around. You'll notice that everything over here, pretty much, except for a couple of exceptions, is brown, all right? And that indicates a fast racetrack condition, all right? How can a racetrack be fast? Well, it's conducive to horses running quickly, all right? But once we start getting into the mid-120s, we have some green popping up here, which means good. And we have some purple, that means sloppy, some red, that means slow, and a couple of fast tracks over here. But one thing to note, by and large, this first mode consists of fast tracks. This mode over here consists of a diverse set of tracks, some of which are good, the brown ones and the green ones, some of which are bad, the red and the purple ones, or the yellow, which means heavy. I don't even know what the difference is between muddy and heavy, but there you go. So that's what's going on here. I would consider there to be a mode at the 128, 129 second mark, just because the data in this region are fundamentally different than data in this region. There's more variety of things going on here than over here, which is by and large fast tracks. Now, I said in my last lesson, I think there was a rule change, and I don't know, you can research the Kentucky Derby to figure out whether that's true or not. But there is a fundamental difference between what's going on here and what's going on here. Because we have fast tracks over here like we have over here. We have good tracks, a handful. I think those are both green right here. We have some good tracks as well, but the time is a lot longer, especially for a horse race. That's a lot longer. So I think there was a rule change at some point. The track was maybe made a bit longer for a period of time or shorter for a period of time. I don't know. So maybe like this is when the track was shorter. This is when the track was longer. I have no idea. All right, let's talk about the shape of data, different distributions, right? The first distribution I'm going to talk about is the uniform distribution. All of the bars have about the same height, no very high highs or low lows. Sure, the boxes are of slightly different height, but they all seem to vary between 40 and 60, oscillating here and there. Not a huge difference and no clear modes. Well, is this a mode? Well, it's so close in height to its surroundings that I'd be hard-pressed to call that a mode. Okay, so that is a uniform distribution. All bars have about the same height when displayed in a histogram. Now we're going to talk about a symmetric distribution. All right, there are several symmetric distributions, but the most famous one is often just casually called a bell curve or the bell curve. And more formally goes by a couple different names. We'll learn about two specific bell curves this year, the curves that have obviously this bell shape right here. One of them, the most famous curve in all of statistics and debatably in all of mathematics, is called the normal or Z distribution. All right, we will talk about that a lot this year. All right, debatably the most important distribution or curve to model data in all of mathematics. So that's a big deal, the normal or Z distribution. Another one that shows up a lot in AP Stat is the T distribution, which is similar to the normal or Z distribution, but it has a really neat feature that makes it convenient in some circumstances. So we'll talk about the T distribution late in the year. Okay, so these are kinds of symmetric distributions. The bars in a symmetric distribution display bilateral symmetry, right? It does not necessarily need to be bell-shaped, all right? If we have bilateral symmetry, say our distribution makes a U kind of shape, all right? That is a symmetric distribution. And there are aspects of symmetric distribution that symmetric distributions share regardless of their precise shape. But as I said, the most important symmetric distribution you're going to run into is this bell shape right here, all right? A symmetric histogram can fold in the middle so that the two sides almost match. There's a theme in statistics, and it's that nothing is really perfect, all right, especially when we're dealing with real-world data. We'll actually talk a little bit about when data look too perfect. That's actually a problem, all right? That's not a good thing. That's actually a big problem. It means someone's been messing with data, all right? So we'll talk about that later on. But with a symmetric distribution, you can fold the data about an axis of symmetry, and they'll lie on top of each other, all right? This distribution is symmetric and bell-shaped. In other words, it is approximately normal. That's that normal distribution I was talking about. The normal distribution, as I said, is the most popular and useful distribution in statistics and debatably in all of mathematics. Now we're going to talk about the interesting cousins of the unimodal bell-shaped symmetric distribution. All right, these are the odd cousins of that. We have the left skew and the right skew. Now, these are very easily confused because left skew has most of the data on the right, and right skew has most of the data on the left. What gives? Well, we get the name left skew because, admittedly, most of the data are on the right, but here's where the name comes in. There is a longer tail on the left, all right? We name these curves by their tails. Now, what on earth is a tail, all right? This is the area associated with the mode. The parts of the distribution furthest from the mode that still contain data are called tails. All right, so we have a tail on the right. Oh, hum diddly do. That's nice. But then we have a tail over here that is significantly longer. Okay, there's much more going on the left than on the right. So we would say the data are left skew because there is a tail on the left. Right skew. Most of the data are on the left, admittedly, but there is, again, a longer tail on the right. Okay, so we have our modal class here, and we have a little tiny tail to the right. We have a little corgi tail over here. And then we have a brontosaurus tail here out to the right, okay, with a couple of possible outliers. We'll talk about that in just a moment. Yes, those are little tiny bars there that are mega outliers. That happens a lot when we're dealing with money. Money almost always produces outliers, okay, unless you really mess with data, and we'll talk about how to legally mess with data later on without corrupting it, all right? So sometimes you can get rid of these outliers in money cases, but in this case, yeah, we're just going to let them sit. This is a right skew distribution because there's a longer tail on the right-hand side. Now we're going to talk about unusual features. We've talked about modes. We've talked about the shape of data. Now we're going to talk about unusual features. And the most common unusual feature is an outlier. Okay? So an outlier is a data value or are data values. There can be more than one outlier far away from the body of the distribution. Here be the body of the distribution. This little bar right here corresponding to a frequency of 1 on the far right-hand side, that is an outlier, all right? The data are not well described by this point right here, and it's possible that this one data point was erroneously entered. Maybe someone intended to write 10.5, but instead wrote 15.0, got some numbers confused in their typing, all right? That is certainly possible. Or maybe this is a legit data value and it's worth our consideration, all right? There is a more technical definition of an outlier than just, oh, it looks a little different, but we will discuss that shortly. Outliers can be important, but they can also indicate errors, all right? This may be an important data value, or this may be 10.5 typed in incorrectly. Either way, they're always worth noting when analyzing a set of data. Now we're going to look at this set of data dealing with money. So, as I said, we shouldn't be surprised to see a couple of potential interesting data points way out here on the right-hand side. A credit card company wants to see how much customers in a particular segment of the market use their credit card. They have provided you with data, footnote you can find in your textbook, on the amount spent by 500 selected customers during a 3-month period and have asked you to summarize the expenditures. Of course, you begin by making a histogram. Of course you do, good statistics students. Describe the shape of this distribution, right? Now, is this distribution unimodal, bimodal, or multimodal? I'm going to go with unimodal because there's only one mode, right? This guy is the modal class, somewhere between, I think these intervals are going to be 400, so you got 400, 800, 1200, 1600, all right, and good. So these are intervals of 400, just had to check myself there. So somewhere between the 0 to 400 class, that's going to be our mode, right? And cool. So that's going to be our one mode. And you may be thinking, what about this right here? Does this constitute a mode because it's a separate little bump here? I'm going to actually debate that's an unusual feature. We'll get to that in just a moment. Left skew or right skew. All right, let's look at the tails. Here is our modal class, all right, the class 0 to 400 that has the highest frequency by a lot. And let's look to our left. All right, there's a little tiny corgi tail over here. And to the right, we don't have quite a brontosaurus tail, but at least, I don't know, we have some tail that's bigger than a corgi tail, all right? I don't know, a husky tail or a golden retriever tail, all right? The tail is bigger on the right-hand side. So I would say that this is right skew. All right, this is right skew. The vast majority of the data are down here, but there is a bit of a tail on the right-hand side. Now, mind you, I'm just talking about the bulk of the data. I'm not talking about these outliers. These may be outliers. That is definitely an outlier, okay? Speaking of outliers, are there any outliers? Yes, there are absolutely some outliers. This is an outlier right here. With money, outliers are almost guaranteed, okay? Anything else interesting that we're seeing? One of the bars seems out of place, but might make sense. I'm not talking about the outliers or potential outliers here. I'm talking about this bar. You'll notice that there's a 0 here, which corresponds to 0 average monthly spent on a credit card. What's going on here? How can we possibly spend less than $0 on a credit card? Well, if you know how credit cards work, sometimes you might make a purchase using a credit card and you may need a refund, okay? And say, I don't know, I'm making this recording in August. Say I made an expenditure on my credit card and it was the only one over the course of the month. And then within my 30-day period of time where I can return the product, I return my product. I'm not satisfied with it. I'd like my money back. Well, that money would be put back onto my credit card balance, but since it would then be September, my total for September would be negative. I've spent negative money because I haven't spent any credit card, we're assuming for the sake of this analogy, but I got a refund. And it was a month later about, okay? So within that 31 day period where I can return my product. So it is possible to have a negative amount spent in a credit card if, for the month of September, I were not to use my credit card for any other purchases and I got refunded for something that I bought in August. All right, so it is possible to have a negative amount spent on a credit card. It actually just means someone has refunded you. Now we're going to talk about the center of the data. So we've talked about modes, we've talked about the shape of data, we've talked a little bit about some unusual features within the data, and going through, we now have to talk about the center of data, a different center than the mode. All right, so we're going to talk about the median now. One way to measure center is the median, which we can understand in two ways. First off, it's the data value that, after the values are ordered from least to greatest, divides the data set evenly. And number two, the data value that divides a histogram into equal areas. All right, so we have a more geometric understanding of what the median is and a strictly arithmetic way of understanding what the median is. All right, so I have two sets of data right here. You have certainly found medians before, so I'm not going to insult your intelligence. I'm just going to do a quick example here, and we'll move on. So we're going to find the median of this first set of data. You will notice these numbers are a little bit out of order. So what I'm first going to do is put them in order and then count to the middle. I see that 4 is in the middle, so 4 is my median of these data. My next set of data has an interesting little feature. My first set had an odd number of values. There are 7. But this set has an even number of values. There are 6. So again, I have to put them in size order here. I start with 2 going all the way up to 11. And then I see that I have 2 values in the middle, this 4 and this 6. They're both occupying the middle spot. So I find the mean of 4 and 6. So 4 plus 6 divided by 2, and that's going to be 5. So even though 5 is not a value in my data set, unlike up top, 4 is a value in my data set, that's my median. Even though 5 is not a value in my data set, it is still the median. All right, quick example, not going to insult your intelligence. We'll move on right now. Okay, this you may not know. This you may know, but I want to give you a little trick for how to conveniently find the median when you're working with sets of data that have more than 6 or 7 values, which is a lot, okay? Let n be the number of data values in a set, all right? And we're going to assume n is a pretty big number. You can't just conveniently count to the middle like the examples over here, all right? Note that if n is odd, the location of the median is the value in the position n plus 1 over 2. So let's use our examples over here because they're nice and easy, all right? There are 7 values here, all right? So n is 7. The median is going to be at the location 7 plus 1 over 2 after ordering the values from least to greatest. 7 plus 1 over 2 is going to be 4. Well, I count 4 data values, 1, 2, 3, 4. Isn't that convenient? And so 4 happens to be the 4th data value, so that is our median, all right? So now we note that if n is even, so we have an even number of data values, then the location of the median is the mean of the values in the positions n over 2 and n plus 2 over 2. We can also understand this as n over 2, pause for emphasis, plus 1, okay? But n plus 2 over 2 is maybe slightly more convenient to write. Okay, so let's look at our example over here with an even number of values. I've made them least to greatest right here. There are 6 values, so n is 6. N over 2 then would be 3. N plus 2 over 2 would be 4. All right, so the 3rd and 4th values in that set, I want to find the mean. Well, the 3rd value is 4, and the 4th value is 6. The mean of those two numbers is going to be 5. These formulas are great to keep on hand when looking for the median. Otherwise, you're going to be doing a lot of counting, and especially when your data sets are in the 20s, 30s, 40s, and so on, you're going to want a quick, convenient formula to do this, all right? Just like these examples, all right, that we're going to be getting to right now. What is the median data value according to the graph below, right? On the x-axis, we have some kind of score, so the score is what we're analyzing, and then we have frequencies of how many people got each of those scores. All right, so take a moment, see if you can find the median, pause the video, unpause when you think you have an answer. Okay, I'll assume we're ready to go. Let's see what the answer is. So I'm going to count these data values. I have 2 here, I have 5 here, so that's 7 plus 4 is 11, 12, 13, and 14. I have 14 data values. That's an even number. So using the formula from the prior slide, I'm going to find the n over 2 and n plus 2 over 2 values. All right? So n is 14, n over 2 is 7, n plus 2 over 2 is 8. So I'm going to find the 7th and 8th data values starting from lowest to highest, right? So I have 2 1s and I have 5 2s. So this would be my 7th data value right there, all right? So my 7th data value is a 2 and my 8th data value is a 3, okay? So the average of 2 and 3, the mean of 2 and 3 is going to be my median, which would be 2.5. So if you got 2.5 for your answer, you are correct. You could, of course, count to the middle, but with a histogram, that is a little bit of a headache. So using that little formula that I gave you is really nice. Now we're going to look at what is called a grouped histogram, all right? A histogram for grouped data. What that means is that the classes don't just correspond to one data value. These classes correspond to one value. This class only has scores of 1, scores of 2, 3, 4, and 5. But these classes have scores of, or heights, that is, of 58 to 60, 60 to 62, 62 to 64, 64 to 66, and so on and so forth. All right? So these classes right here correspond to more than one possible data value, so we'd call it a histogram for grouped data. All right, so within which interval, all right, within which of these groups of data could we find the median of the data set? This one's a little more tricky. Try this one on your own. Pause the video. Once you think you have an answer, unpause the video and see if you got it. Okay, I'll assume we're ready to go on. Some of you may have counted each of these bars, but If you were looking carefully and wanted to know how many total students there were, the problem says as much. 25 students. There you go. So this is a frequency distribution for the height of 25 students. 25 is an odd number. Going back to the prior slide, we use the formula n plus 1 over 2. Okay? So 25 plus 1 is 26, divided by 2 is 13. So we're looking for the 13th data value. All right, let's start counting. 1, 2, 3, 4, and then we have 5 here, and then another 5 would make 14. So one of these data values in here is going to be my 13th data value, and that would be within the class 64 to 66 inches. So within which interval could we find the median of the data set? Well, it's going to be somewhere in the 64 to 66 inch range, all right? Somewhere between, if you speak British imperial units, if you're international, I'm sorry. If you speak British imperial units, somewhere between 5'4" and 5'6". All right, now we're going to talk about the range. Home on the range here with the cows. Recall that statistics is the study of variation. That's something we talked about on day 1 of class. That involves not only the shape of the data and where the center is, but how far out the data are spread. All right, so the spread of the data is a very important, sometimes the most important topic of inquiry. One measure of spread is the range, which is the difference between the highest and lowest data values. It is very, very simple. So we're going to find the range of these data right here. All we need to do is find the lowest and highest data values and subtract them. 9 minus 1 equals 8. So the range of the data is 8. Okay, great. We have now understood how to find the spread of data. Wait a second. Is there a pitfall to using range? The answer is a resounding yes. Okay? Here's an example I made a long time ago about why the range is usually not that convenient in statistics. Okay? So, we're talking about, I'm making this during an Olympics year. This is the famous Michael Phelps right here. Basically what Simone Biles is to the current generation, Michael Phelps was to my generation. All right, so you have your friend, your other friend, your friend who doesn't swim as well, and your friend who was on the swim team for 2 years in middle school, and you got my man Michael Phelps, all right, who that was a world record time for, I forget which event, but it was a world record time for one of Michael Phelps' events that he swam in. Right? So here is a great example of pulling some data from Mike Phelps and making up some data of my own that help describe why the range is not that great in statistics. All right? The range of this data set is about 12 minutes. Right? This spread is made exceptionally large by the outlier that is Michael Phelps, and possibly your friend who doesn't swim well, but definitely Michael Phelps, who skews our data. All right, skews our data just means it's a value that there's an outlier, and the outlier is going to change some key metrics of our data. All right, and the further we get through the year, the more you'll see that an outlier can really mess with the center and spread of the data, which are very important for us to know. Okay, so if you were to get rid of this outlier that is Michael Phelps, you have a range of about 7. All right, you throw Michael Phelps in there, your range goes to 12. That is a massive change, and only one data value did that. Okay, the problem with range fundamentally is it only cares about 2 data values. It only cares about the highest data value and the lowest data value, and it completely ignores all of the other data values by definition. A measure of spread that takes into account more data values is preferable. We're going to learn about 2 such measurements, namely the interquartile range and the standard deviation. The best measure of center The vast majority, the best measure of spread, the vast majority of the time in statistics is the standard deviation, all right? But there are some cases in which the standard deviation is not appropriate for the data set, and then we will use the interquartile range,